Hi, in this video, I'll be continuing our journey in calculus where I show you more functions that are integrable and we can build our foundations before I show you in the next video different techniques of calculus to integrate different types of functions. But we need to build our foundations first and we'll now carry on. So in the previous video, let's do a recap. We have already went through the fundamental theorem of calculus where we realized the importance of finding antiderivatives so that we can evaluate definite integrals easily. And these definite integrals have applications that we want to use, such as finding the area under the graph as a simple example. But now we want to construct more and more functions that are integrable. And one function is if you have a function and you are able to find its inverse, you are also able to show that this inverse is differentiable. And this gives you a way to differentiate inverse functions. And then you can just take the integral of, then you are able now to determine what are the integrals so that you get back this inverse function. So let's take a look. So to understand it, we realize that inverse functions are bijective, and so they are both surjective and injective. And by being injective, being one-to-one, they are monotonic and continuous. So suppose you have this continuous function, then its inverse is also continuous. And it's fairly easy to prove because you just take, to prove that it's continuous, you need to show that the limit of f inverse at a equals the limit as x approaches a of f inverse x equals to f inverse a. But f inverse a, if you were to substitute this limit of x, it's just making, for example, this. So the proof of this theorem is already shown in the textbook, so I won't really go through it again. But just understand that if you draw a graph, the inverse is just a reflection about the y equals to x. So if you're continuous here, then each point of this you reflect over, you'll be continuous as well. So because there's no breaks here, there won't be a break in the inverse, in the reflection. So that's why it's also continuous. That's the geometric understanding. If you're differentiable, then your inverse is also differentiable. But the most important thing is that it's related by this equality. So the inverse derivative is 1 over the original derivative. And that is important to understand because now it gives you a way to evaluate the derivative at a point for an inverse function easily. So the first method, of course, so this proof is also given in the textbook, so I won't go through again, but I hope you understand from the picture that if you are able to draw a tangent line on the graph and you reflect it, you're also going to be able to draw a tangent line on this point as well. So, but more importantly, we want to talk about how we want to use it in our questions. So suppose you have a function fx. The inverse is of course square root x. And so if you take the derivative is 1 over 2 square root x, and then you just evaluated it at the point 2. And that's 1 over 2 square root x. But you realize that with this now, you don't need to evaluate this, the inverse function's derivative explicitly, but instead you can find the point where fa equals to 2, meaning a equals to square root 2, and then you evaluate f prime square root 2, which equals to 2 square root 2, and so f inverse prime 2 equals to 1 over f prime square root 2, which equals to 1 over square root 2. And you can see that they are the same. So this allows you to find the f prime of the inverse function without explicitly finding the inverse function. And we can apply this to sine inverse x to get 1 over square root 1 minus x squared. And now we are able to integrate these functions, 1 over square root 1 minus x squared. And that will be just sine inverse x. Similarly, the derivative of cosine inverse x is minus 1 over square root 1 minus x. And so when you integrate this, you get cosine inverse square root x plus c, of course. And so now this gives you more functions that you can integrate. So now you know you can integrate this form to get sine inverse. Of course, sine inverse square root x has its own integral, but we won't dive into that for now because it requires more techniques of integration to get. But I hope you understand how, because you have proven now inverse functions are differentiable, you can differentiate inverse functions and integrate what is this derivative to get the inverse function. So the proof of why this follows, I won't show because again it's in the textbook, but instead I'll show you why the derivative of tangent inverse x is 1 over 1 plus x squared. And basically it's actually the same application to how you prove this. So you just let y equals to tangent inverse x. So x is just tangent y. You differentiate it with respect to y, you get secant squared y, which is honestly the same as 1 plus tangent squared y. So dx dy equals to 1 plus x squared already. And then you just take dy dx will just be 1 over dx dy. And that's just 1 over 1 plus x squared. And so you've proven it. So it's that simple. Other common functions that are noted is the power function, which we've done in many cases earlier on. And so if you integrate the power function, it's just x n plus 1 over n plus 1. Because you need to bring down the power, which will remove the denominator as well. And then minus 1 the power, so you just get back xn. So this is verified. So you want to verify an integral is really just differentiating the antiderivative and see whether you get back the original function. Of course, the derivative of sine is cosine x, which means the integral of cosine is sine x. I've already said about the derivative of sine inverse x. But now the question is, how do we want to find the integral of tangent? We know the integral of secant squared x will be tangent x, because if you differentiate tangent, you get secant squared. But how do we want to now integrate tangent x? And this idea is realizing that tangent is sine x over cosine x. And the derivative of cosine x is minus sine x. And so you can realize that the top now is f prime x somewhat, and the bottom is fx. And we want to see whether there is an integral in this form. And that led mathematicians to develop the idea of integrating 1 over x. So we know that the integral of x to the power minus 2 dx is 1 over x minus 1 over x. And that's because if you differentiate, 1 over x is minus 1 over x squared. But when you x to the power minus 1, you can't differentiate an x to the power of 0 to get x to the power minus 1, because that will be you're differentiating a constant, which is 0. And so we need to define a new function, and this is known as ln x. So we define ln x to be the integral of 1 to x of 1 over t dt. And so this ln x is both continuous and differentiable. And so when if you use the fundamental theorem of calculus, it means when you differentiate ln x, you get 1 over x. And the ln function can be looks something like this with an asymptote at x equals to 0, and it cuts the graph at ln 1. So ln 1 is defined to be 0. Because integral from 1 to 1 of 1 over t dt will be 0. And you can prove certain properties, such that the ln of a constant times x is just ln a plus ln x. Ln x to the power r is r ln x. And I'll just show you the simple one for proof of 1, and it's the same for proof of 2. What you do is you recognize here as x and here as x, so you bring this over, and you want to show it's just ln a, which is a constant. So you just take fx equals to ln ax minus ln x, you differentiate it and show that it's 0, and so it's a constant. You evaluate the constant at 1 to get because it's easier to evaluate, and you show that ln ax equals to ln a plus ln x. And a similar idea is to prove this by taking the function of ln xr minus r ln x and show that it's 0. So it's very simple. So, but we also want to say that if x is less than 0, the derivative of ln minus x, which is now defined, is minus 1 over minus x, which is 1 over x. And you can see that whether x is positive in the definition or x is negative, the derivative of ln x will always be the ln of the positive value of x will always be 1 over x. And so we can say that whenever x is not 0, the derivative of ln x, so we need it to be positive, so we put a modulus, will be 1 over x. And thus, when we integrate 1 over x, it's actually not just ln x, but ln modulus x. Because, remember, in these cases, we are restricting it to greater than 0. But if we want to just integrate indefinite integral, we need to find its antiderivative. And its antiderivative is differentiating this for all its domain. And so, now x can be defined for an entire real line except at 0. And we see that the integral of 1 over x will just be ln modulus x. And generally, you can then generalize it to integral of f prime x over fx will just be ln modulus fx. And this really follows because if you differentiate it, it will be 1 over fx. And then by chain rule, you need to differentiate fx, which is f prime. So you get this. And this now shows how we're going to integrate this form of functions. And that gives us a way to integrate tangent x. And this shows that it's minus ln modulus of cosine x. So you just got to remember the modulus unless the domain is specified and then cosine x is strictly greater than 0. Because the ln function only works on x's greater than 0. With this, now you are able to integrate functions of this form. And then we want to say that because we already know this is continuous and differentiable, and it's monotonic, which you can show, it now proves that there is existence of an inverse function. And this inverse function is known as the exponential function. And because it's increasing and it's 1 to 1, there will exist a unique point on the graph such that ln c equals to 1. And this c will now be known as Euler's number E. Why do we care about the 1? It's because when we take a function and we run it through its inverse, it will result in the identity map. And so that's why 1 is like the identity. And so by definition, there exists a unique y such that ln y equals to x. And so now we just take y to equals to ex. And this is known as the exponential function and is defined from all real numbers to the positive real numbers. And then we also know that ln x and ex are inverses of each other. You can prove its following properties, and then we can also define the exponential of base for any base to be e to the power x times ln x. And what's really cool about this exponential function is you're able to show that the derivative of the exponential function is the same, and told the integral of ex is just ex plus c. So now this is really very important in building mathematics, and the derivative of it shows that an ex is the only function such that its derivative is itself. So it's pretty cool, I would say. And with this, we are able to build our understanding of hyperbolic trigonometric functions. And really what we want to just show is that we are just defining more and more functions so that we have a greater dictionary of functions that we can integrate from. So the hypergeometric function is known as sine x, sine with a hx and cos x. And it's defined to be ex minus e to the power minus x over 2, and the other one is ex plus e power minus x over 2. And why they are called hyperbolic trigonomic functions is really because they have the behaviors of a trigonomic function. Such as when you differentiate side x, you get cos. But when you differentiate cos, instead of getting minus side x, you get just sine hx. And then you are able to find its inverse and differentiate that well. So now you really get a slew of functions that you know how to differentiate from. Similarly, for cos x, you are able to get cos inverse x and differentiate it to get this. All this now gives you multiple antiderivative of very common functions that you use when you do applied mathematics. And so you just need to keep practicing to get familiarized with what it is, and soon enough you're able to tell me the integral of sine squared x dx. And so I've really come to the end of this video, which is just showing you all the different type of functions that you can integrate with. And in the next video, I'll show you techniques to integrate more functions, where we now combine maybe ex sine x, and we want to know how to integrate these form functions, where it's a combination of both the exponential and trigonomic. And you can just play around with different things and keep practicing using the textbook or any notes that you have to supplement your learning. And that's really how you get better in practicing differentiation and integration multiple times. You can also watch a YouTuber that I very like. It's named Black Red Pen, and then you can just watch him quite often. So Black Pen Red Pen is a very good YouTube channel that I recommend you watching if you want to see how you practice calculus often. And in the next video, I'll show you more techniques of calculus, where now we will combine all the functions that we know to integrate them better. Thank you for listening to this video, and I'll catch you in the next one.